We can go back to the slides. That was the first demo. So the second demo is about a traction inverter. Traction inverter is a device used often in the automotive industry. It's a power electronic device where you basically convert direct current to alternating current and vice versa. And, you typically have IGBTs that get pretty warm, and you need some kind of forced cooling to bring, the temperatures down to reasonable values so the whole thing doesn't melt. In this demo, we're going to use the following materials. So a fluid, the fluid's going to be water, the housing is going to be structural steel, IGBTs are going to be silicon. We have our boundary conditions here. So the external convection is going to be coefficient close to what we would expect from natural convection. So this value here, 3 watt over square meter Celsius, and an ambient temperature of 22 degrees Celsius. Then we're going to set heat sources on all 4 of the IGBTs, equal to 400 watts, so 1,600 in total. And we're going to have an inlet flow at 2 meters per second and 25 degrees Celsius to cool the whole thing down. So that's our forced convection. And then we're going to have an outlet at 0 Pascal relative pressure. Good. So let me jump to that second demo. Here we can see the traction inverter. You can see the complexity of the IGBTs here. Let me just select them from the geometry. In reality, they'd be a lot more complex than this. You probably have, PCB on it and a bunch of different chips and whatnot, cabling and everything. But here we just blocked them all together because this is really a conceptual tool meant for, early phase, meant for the early phases of product development. So, the amount of complexity and the type of questions that you can ask and answer with ANSYS Discovery are indeed not too advanced in that sense. I mean, here you can just understand pretty much the cooling power that you need, and you can modify a bit the cooling channels to understand, which concept looks the best. So heat up a heat source. We can put that at 1,600 watt. And then I'm going to also change the materials here. Just a sec. Set this to silicone and volume extract part. So here we said it was 2 meters per second. Then we wanted 25 degrees Celsius. On the out, 0 Pascal, and a recirculation, we just leave it at 22 degrees Celsius. And that is pretty much our calculation set up. You can see here in the physics tree, we got our solid thermal boundary conditions. We have our fluid flow boundary conditions. We have our connections, so bonded contacts between the solids, and then our fluid-solid interfaces. So let's start the calculation and see if the maximum temperatures are lower now and hopefully around a more reasonable value that won't melt everything. So here we have, as you can see, we're around 75 degrees Celsius. We can look at the outer temperatures. If you hover over a certain location with your mouse, you get the exact value on the color scale. So here you can see the top IGBT is indeed the hottest component. It's around 75 degrees Celsius. You can actually also show maximum and minimum locations. So maximum's up here on the IGBT, minimum is somewhere down here, or in the fluid flow itself, probably, close to the inlet. And then on the bottom here, you can see we have, much cooler IGBTs. So, the efficiency of this cooling channel is probably not as uniform as it should be. You could probably consider redesigning it so that you have maybe a couple more zigzag channels passing underneath this upper IGBT to cool it down a bit more and get it a little bit closer to the temperatures on the bottom. So that's some kind of design variation that you might want to consider. In any case, you can see, these maximum temperatures now are at much more reasonable values. So here we can see, why we need some kind of internal forced convection, in this case, liquid cooled, and that's basically what's being used in industry today. A lot of your automobiles probably have this device in it too. Good. So the last demo I want to show you, today is, again, this IGBT, and we're going to be looking at pure isothermal fluid flow calculations just to try to optimize a little bit better the cooling channel itself. So I'm going to do a volume extract here. So we have our volume extract, then I'm going to set this to transparent, and I'm going to show you guys here in the geometry tree that from our native CAD system, we've brought in basically different designs that we want to explore. Here you can see kind of, horizontal cooling channels, ribs, then we have vertical ones, then we have some pins, and as the last one, there's these super thin channels that are basically guiding the flow all the way from inlet to outlet. And so we just want to see which one behaves the best in terms of, recirculation zones, pressure drop. If you have too many recirculation zones, those are kind of areas where you're losing potential energy from the flow to extract heat from your system. So you want to kind of avoid those if possible. So, just visually, we're going to look at where those are and how we can, and which design variation looks the best. So let me set up the fluid flow, then we can look at it from the top. Start up our calculation. Let me do these little kind of weightless particles that are showing kind of the fluid flow. Here you can see the first design, of course, no real obstacles between inlet and outlet. It's letting the flow pretty much do what it wants to do. And, we have a big recirculation zone here, so that's probably not the best design. I'm going to activate now the first rib design. This is actually the one that we had in the previous CHT calculation. I'm going to update the volume in context, so we get an immediate fluid volume update based on the, geometrical change of the solid. And here we can see how that impacts our fluid flow. Looks a bit better. Of course, this big recirculation zone here that we had before is not there anymore. We can look in terms of pressure drop. Yep, it went up. Since we're adding more obstacles between inlet and outlet, you need a little bit more power to pump water through this system. Then we have the vertical ribs. So let me update the let me go ahead and update volume in context. And here, basically with pins, you're not going to have that high of velocity in between the pins itself, but you're going to increase probably surface area for heat exchange. So that's something that you can take into consideration also when you're doing these types of calculations. Pressure drop has actually been lowered a little bit compared to the design before. So, to completely validate this afterwards, you would have to insert again the other solid components, the IGBTs, and do a full-blown CHT calculation to see the behavior of the full system. Let's go back to these slides. And this brings me to the end. So just a quick overview of what we did the last 20-25 minutes. We saw that ANSYS Discovery can solve numerous fluid simulations, steady state flow, transient flow, incompressible, compressible flow, porous media, and conjugate heat transfer. The current capabilities that we do have, as I mentioned before, we are adding new features continuously since it's a pretty young tool in the ANSYS portfolio. So, from one year to the next, you might have quite a few new features being added. Then we saw two demos today, one with a mixer T and a traction inverter, where we kind of explored, we saw firsthand how to set up a fluid flow, first of all, important steps, extract the fluid volume, set up your boundary conditions, set up any monitors that you want to track, and, visualize your results. And then, as a last recommendation from my side, ANSYS Discovery is very useful for upfront simulation to understand general trends in your setup. It's great to quickly modify or parameterize geometries and boundary conditions thanks to direct modeling that's running in the background. And, hopefully you saw today live, how instantaneous the feedback is and how the visualization of the results are quite easy to toggle in between and change. So definitely for the academic world, it would be a nice tool to use for teaching, in our opinion. That brings me to the end of my presentation. I'm going to hand it over to the next presenter.
Yes, so thank you very much, Chris. These were two great examples demonstrating the fluid capabilities. And now I just want to round up our presentation today, sharing a success story. So obviously you've seen today that we are really enthusiastic and excited about the software, but it's a bit more independent if it comes from an academic providing this feedback. And so at the University of Michigan, Professor Masoud Kaviani has actually been using Discovery to teach his class on heat transfer, specifically covering topics and assignments on three-dimensional steady state, conduction in composites, as well as an air-cooled heatsink, looking specifically at fin efficiency and the Nusselt number, just to give you an idea as to how it could be used. And he was specifically looking at comparing exactly the analytical with the numerical results. So what we've said at the beginning to basically complement physical phenomena and analytical education. Now, as you can see from the post-student survey here on the bottom, most students fully agree that Discovery is a useful tool for helping them learn the subject. Obviously, there's always someone who doesn't agree, so we have one person disagreeing, but of course, you cannot please everyone here. But just a nice success story that we wanted to share with you. Now, before we open up the stage for the discussion and question and answers, just wanted to share a few slides on the supporting resources that we supply alongside Discovery. Starting off with the webinars. So similar to today's webinar, we have many more Discovery webinars available on demand on the ANSYS Resource Center. New webinars are added frequently, so it's always a good idea to look at our academic landing page. We've provided a selection here of the most recent ones, and again, if required, we can share those slides after the webinar, and you'll be able to click on all those hyperlinks. Next, I would like to draw your attention to the Discovery Forum, which is a great repository for information, knowledge, and skills. So you can go there independent of your familiarity with Discovery. You'll get technical assistance in the FAQ section and tech support requests. As you can submit those as well. And if you haven't yet tried Discovery, or if today's webinar has increased your interest in using it, you are able to get a 30-day trial version as well for download, and you find all the information in the ANSYS Discovery Forum. In addition, we provide a range of different AICs. So these are the ANSYS Innovation courses, which are free and award-winning online courses for all the main physics and all the software that we support. So in terms of Discovery, you'll find courses and tutorials guiding you through geometry preparation, structure analysis, thermal, and fluid flow simulation as well. So always worth having a look here. Similar to the ANSYS Discovery Forum, we have the general ANSYS Learning Forum for the different products. So here on the top left, you can see the 3D design section, which is associated with Discovery, where you can learn new skills, find answers to certain questions from other peers or our ANSYS experts as well. Lastly, I would also like to really highlight our endeavor in terms of education resources that our academic development team is creating. These are free to download on our website as well. Currently, they are covering fundamental topics in engineering with ANSYS Discovery in the form of lecture units, as well as application-focused case studies. These can be easily integrated in your existing slide decks for teaching, or just can be used as inspiration. So here's a selection of the ones we have free to download at the moment. There's a lecture unit of beam analysis, stresses and strains, an introduction to CFD, and a design study on a chair. As you can see, we're expanding the resources constantly. So something that is upcoming very shortly is a flow over an airfoil, an introduction to FEA, as well as heat transfer. And just to give you an idea as to what you can expect in these education resources and how they can be used. From a structural aspect, here are a few snapshots. So you might be looking into principal stresses or equivalent stresses in the early engineering courses, stress concentrations or beam theory in the first few semesters in engineering education, computationally into mesh refinement, convergence studies, or if you're interested in looking into the difference of different materials on structural loads or Poisson's ratio, that's also possible here. And likewise, if you're dealing with CFD in your teaching, we've shown you today that it's really easy to visualize flows, looking at different types of flows like steady flow, unsteady flow, rotational flow, or just general internal and external flow. And yeah, it lends itself really nicely when it comes to teaching, for instance, Bernoulli equation, where you look at conservation of mass or conservation of energy. And likewise, it also allows you to easily scope through the effects of using different fluid media. And with this, we have actually reached the end of the presentation, and I would like to really thank you everyone for attending. There's basically nothing left for me to say, but if you want to get in touch and want some more information, today's slides, if you're interested in a personal demo or learn more on the education resources, please feel free to leave your interest in the chat or get in touch with us directly. With today's speaker, Nick Stefani, who's the Academic Content Development Manager, his email is provided here on the slide.